There we go. Okay. So folks, we have this differential equation, and I'm going to just go ahead and comment this in here. So we're looking at y double prime plus xy prime plus y is equal to 0. And the initial conditions are y at 0 is 1 and y prime at 0 is going to be equal to 0. Okay, so first thing I always do, CLC and clear all. Okay, so that way we just kind of have that set up nicely. Okay. And then what I want to do is I want to get the exact solution for this thing first. Okay, so we already did that on assignment 1, and I showed you guys how to do that, but I'm just going to remind you because I'm assuming not everybody in here has been religiously doing MATLAB since the last assignment, which I wouldn't expect you guys to do. Okay, so I'm going to make a couple symbolic variables. So I'm going to have a sims x and a y at x. And then I'm going to call the equation, I'm going to have a dy. And dy is going to be equal to diff y comma x. Okay. So my equation, I'm going to call EQU, is going to be equal to our second derivative. All right. So I'm just programming the second derivative. So that's diff of y comma x comma 2. All right. So that represents y double prime plus x times diff y comma x. Right. And then finally, plus y is going to be double equal to 0. Okay, so you guys might remember that you have to use a double equals unless you're doing assignment. Okay, all right, now I'm going to solve this. I'm going to program the conditions. So I'm going to say condition 1, that's going to be equal to y at 0 is equal to 1. And then condition 2, and this should be a double equal, excuse me. I just got done saying you have to do that and I didn't do it. And then condition 2 is going to be dy at 0 is going to be equal to 0. Since we have 2 conditions, I'm going to make one more variable called cons, and that's going to be a matrix condition 1 or con 1 comma con 2.
Should you go back and put a double equal?
Yeah, thanks Wesley, good catch. I did the same thing again. Jeez. All right. Last thing I'm going to do, folks, is I'm actually going to solve the differential. Okay, so I'm going to call it solve for my solution. And the solution is going to be equal to dsolve EQU, comma, con z. Okay. All right. Now I can go ahead and just execute this, and I'm going to run this just to show you guys what the solution is. But this, I mean, this should be at least somewhat familiar to you guys because we did this on the first MATLAB assignment. Okay. If you don't remember it, that's fine. I'm not expecting folks to memorize it, and so we get a really nice clean solution out of this, right, guys? Okay. So MATLAB tells me it's e to the minus x squared over 2. Okay. So pretty easy solution. All right. Now, what if we want a series solution for this thing? Okay. And that's because sometimes it doesn't give us a nice compact solution to this. In fact, it might not solve it at all. Okay. So, and if I want to, I can print this out really nice. I can do an f print f. And I could say the exact solution is, I could say %s /n comma solve. Okay, so I'll show you what that does. It just makes it a really nice looking solution. Okay, so the exact solution is this. Okay, so and I don't know, for those of you guys that are going to transfer to like UMBC or UMD or whatever it might be, they're probably going to ask you to do this. Okay, personally, I don't care that much, but you know, I can figure it out, but you know, maybe somebody's just too lazy to figure it out. Okay, now what I want to show you guys is how to get to the series solution stuff. Okay, so I'm going to do I'm going to show you that we can get different series solutions of different degrees. Okay, so I'm going to call this D5 solve. Okay, so this will be like a 5th degree solution. I'm still going to use dsolve, and I'm still going to use EQU, comma cons. Okay, but this is where it becomes different. Okay, I'm going to do apostrophe expansion point.
Oh, that's the function.
So expansion point is going to be what point that we're centered around. Okay, so whenever I ask you guys to find a solution, I say find it about x sub 0 equals 0. Or if I'm feeling really mean, x sub 0 equals 1 or something like that. Okay, so I'm going to say expansion point comma 1 or 0, excuse me. All right? And then I'm going to say order, comma, 5. Okay, so what this does, okay, so this is important right here, is that I'm solving the differential equation about the point x equals 0, and I'm getting a 5th degree polynomial out of this. Okay, so does that make sense, like the order in which this means? Okay, now let me execute this and show you what it does. Okay, raise this up a little bit. Okay, it gives us x to the 4th over 8, x squared over 2 plus 1. Okay, where's the 5th degree? Because I said degree 5. Well, it's an even function, right, guys? Because it's an even function, notice that we don't have an x or an x cubed, and we wouldn't have an x to the 5th power. In other words, C1 would be 0 for those, okay? So if we were to write out the solution, we would only have x squared, x to the 4th, x to the 6th, etc. Okay, so just because you say 5th degree, maybe the 5th degree is 0 for that. Okay, so does that make sense to everybody, guys?
So you're not always gonna get all the terms if it's a
Yeah,
odd function.
yeah, or an even function, right? You might be missing a few of those terms in there.
Like, but when we do, we put the terms.
Yeah, when we do it by hand, a lot of times we're missing some of those terms, like with the Bessel stuff, right? All the Bessel stuff we did was all even, okay? Occasionally we got an odd function, okay? I think one of the solutions on assignment 12 was an odd function. Where you guys had like x cubed over 3 factorial, x to the 5th over 5 factorial, or something like that, okay? Now check this, folks. Well, once I have this one, can I just do this? Can I copy and paste it and call this like D10 solve and just change that to a 10? Couldn't I do D20 and turn this into the 20th degree solution? So in other words, once I have that first line of code there, just change it up, and you just keep getting increasingly larger orders of the function. Okay. Now let me go ahead and execute this just to show you how ugly it is. All right, and then I'll show you guys what to do with the graphs of these things. All right, so here we go. I hope I was sharing the screen the whole time. I'm pretty sure I was, but so here's the 5th degree. Oh, this is our 5th degree solution. This is our 10th degree solution. Okay, and then here is our 20th degree solution. Okay, so pretty cool, guys. And usually when I ask you guys to do it, I think I only ask you guys to write out like 3 or 4 terms, right?
Yeah, so if you said the reason why we don't get a 5th is because it's even, how come we don't get a 10th or 20th?
I don't know. Let me put in 11 and see what happens. Maybe it just goes up to that order. Let me see if I put 11 there, it gives the 10th degree. Yeah, so
then I guess you would have to have D solve 10 and then one more than that.
yeah, so it looks like MATLAB just chopped it off. I don't know why, but it should, maybe it gives it up to the 10th degree, but not including that. All right, so if I wanted the 10th degree, I'd probably put 11 in there. All right, so this would be 10th. Okay, so there we go. All right, and then over here, I would want 21 to get to the 20th degree. Realistically, guys, I mean, even if you put 10 or 20 in there, I'm not going to take off any points for that, just because once you get it to be that large, it's a pretty good representation of the solution. Okay. All right. Now let's see how good of a solution it is. Okay, because we can graph these things, right? And the graph should match up pretty well. All right. So I'm going to ask, this is exactly what I'm going to ask you guys to do. Okay, so just to give me the solutions, okay, and then to plot the solutions. All right, so here's what I'm going to do, folks. I'm going to use easy plot, and I'm going to easy plot the solution. I'm going to do hold on, and then I'm going to easy plot. We call it D5 solve, and then I'm going to hold off. Okay. So what that does is that it just plots the original solution and the series solution of the 5th degree, which is really the 4th degree, right, on the same graph. Okay, so let's see what it does. Okay, they should look moderately close around the origin, but once we start straying from the origin, it's probably going to look a little bit worse. Okay, it's not going to be as congruent. All right, so let's see what we get out of this. All right, so, here we go. Around the origin, it's actually pretty good. All right. Once we start getting to like -2, it starts diverging a little bit, right, guys? Okay. The function that's in, I think the function that's in orange, I think that's the original function, the e to the minus x square function. Okay. Which would make sense because it should have like that catenary sort of stuff going on. Chris, go ahead.
So then as you get closer to the higher degree, it's gonna look more and more like that.
Right. And in
Right.
fact, let me do this. Let me plot D10 solve. Okay, and I'll run it. It should be better. It might take a second to kind of. I don't know if you guys can see it, but there's like a little piece of blue up here. Okay. So it's all like if I don't know if I can zoom in on it, but it's tough to see.
Let's see.
Yeah, but now you can start seeing it. So this is actually pretty good out to here. Okay, so that's pretty good. All right. I'm wondering if the one in blue is the one that's the original function. And the one that's in orange is the, oh, what I could do is I could just do this, right? Let's do this. I'm just going to comment that out. I can see which one's the original.
Oh, that's nifty. I didn't know that part was there.
Yeah. Oh, that's cool. Right. You could just comment everything. And then if you hit this one, Chris, that'll comment everything out. Okay. So this is the original functions in blue. But notice, guys, it only goes up to 1. So that's why we only get like almost a straight line. Okay. It's because like the other one goes up to like thousands or something like that. Okay. So it's just the scale of what we have. Okay. All right. So
Is that why it flipped? It's
yeah.
because it was
right, because the polynomial is concave down, but the original function, it's still concave down, but it's, you know, it's not as, the range of it is significantly more compact. Okay, all right, so we can get rid of that. Let me run it again with 10. And it'll do that thing where it's just going to kind of overwrite stuff. Come on. Okay, but see the blue line right here? That's actually that curve. Okay, so that's what's really going on there.
That's the, what's blue again?
Yeah, the blue one is the original.
And the orange is the series.
Yeah, right. It's still really good. Okay, we would just have to zoom in. I mean, look at the scale here. We're going into like the thousands almost on that scale. Okay, so I have to zoom in. Like if I want to see like the original curve.
Right, of the original function.
Yeah, I'm zooming in. Hold on, I'm getting there. And I have to go to 0. Oh boy, this is a mess. Sorry, guys.
We should see some sort of distribution.
Yeah, we should at some point. Oh boy, this is a pain. Now I'm losing it. Oh, I'm sure I could just change the range of it. Okay, but it's almost the same thing. Huh, it kind of just melds into it. Oh, it could be just because of the domain of this thing right here. Oh, I got it. This is 10 to the -3. I didn't see this. So
We change the scale and make it.
yeah, we'd have to change the range to go from 0 to 1 or something like that. But anyway, but you guys,
From 0 to 1, let's see this.
yeah, the norm, almost that normal curve. Yeah. So, but it's actually pretty cool that like it basically overlays it. Okay. I'm just curious to see what the 20th degree solution looks like. And then we can go on. All right. I could probably eat up a whole weekend just doing this like over and over and over again. All right. So, and then if we zoom in, hopefully we would see the original solution somewhere in here. Oh, this is 10 to the 4th power, by the way, on the y-axis. So this is like what, 10,000 right here. We're not going to see that blue curve at all. So I'm not even going to try. So, but good enough, right, guys? We can model it. Okay, so what I'll probably ask you guys to do for the assignment is do something like where you have to do all of them on the same graph. Okay, so, oh, and I'll show you something else that's kind of cool. So we'll hold on. We'll do D5 sol, D10 sol, and then hold on. D20 sol. All right. I think there's a function legend. And I think what that'll do is that will label each of the functions. So I could just say original or the actual, and then I could say like, 5th degree. You just put them in the order. 5th degree or 5 degree, it's fine, doesn't matter. And then I'm just gonna copy this. I'm lazy. And this could be 20 degree, this can be 10 degree. So let me get rid of this so I can show you guys what I did here. So I think this works, okay, where you do the legend. And what that'll do is that'll label all the curves on the same graph. Okay, so let me execute this. See if it does put up something like that. Come on, MATLAB, you can do it. Oh, I knew it. Yeah, there we go. And so the different colors are now represented, so you can kind of see which function is which. Okay, go ahead, Chris.
So you do hold on. Do you have to do hold on after every single one?
Yeah, you should do hold on because if you don't, it'll jump to a new graph. Okay.
Okay.
What we should also do, folks, is we should have probably put figure 1 here. So that way, like it's because if we had more than one figure, okay, we want them all to show up on the same graph. Okay. So, all right. So does that make sense, folks, as to how to like kind of, I guess, what, and the reason we do this is because a lot of times we want to see like, you know, how many degrees we have to go up to get to a really good approximation. Right, guys? Go ahead, James.
So on the example, 5 was like shaped up,
Mm-hmm.
and then 10 was down, and then 20 was up. Do we have to visualize that and then see like, okay, this one's a better example?
Yeah. And realistically, the higher you go, the better the representation is going to be. Okay. You're right. Each of those actually represents the error for the decimal places. Okay. So like a 20th degree polynomial should be accurate to like the 18, 19, 20th decimal place. Okay. So, and that's one of the things you guys might remember when you did the Taylor series is that that's part of the error when you guys did that. If not, don't worry about it. Okay. All right, guys. Other questions I can answer about this? Okay. Let me show you guys how to do Laplace transforms and inverse Laplaces in MATLAB. This is actually a lot easier. Okay. What did we look at earlier today? Did we have the we had the Laplace of, I think this was one of them we had, e to the t cos t, right, guys? I think that was on the last problem that we had. Okay, so let me show you guys how to get MATLAB to spit out Laplace transforms. It's actually really easy. It's only going to be like 2 or 3 lines of code, right? I'm going to define a new symbolic variable, okay, and I'm going to define a sims of t. I'm going to define my function f to be this animal right here, so expt times cos of t. And then I'm going to use the function Laplace parenthesis f comma s. Okay,
That's what,
all right. So let me explain what that does. Okay, that's going to take the Laplace of the function f and the transformed variable is going to be s. Okay, I can make that whatever I want. I can make that q or, you know, another letter or something like that. But let me run it and show you what we get out of that. I'm going to comment all the other junk out in a sec once we actually get it. Oh, I might need a sim. I might have to do a sims for T and S. So let me try that. Let me comment all this stuff out really quickly, guys. Nope, there we go. Okay, so let's try it again. There we go. Okay, go ahead.
I'm sorry, how did you comment on that again?
Oh, what I did was I highlight everything, and then there's this little button up here, the % sign. That'll comment everything. And then if you want to uncomment it, Josh, there's a little window right next to it, or icon, that gets rid of all the comments. Okay, so this and then this. There we go. Is that cool? We can just do that for the rest of class.
That's great.
Yeah. All right. Oh shoot. I don't know what I did, but I think I just did the wraparound by accident. That's fine. It's not that big of a deal. Okay. So guys, that's how you find a Laplace in MATLAB. Okay.
how do you get to the function from there?
Well,
Like do it
Why?
inverse.
How do you get the y from that y? You have to take the
oh,
inverse.
we
of
take the
that,
inverse, right?
Right, so how do you do the inverse?
I'll show you in a sec. I'm going to do one more of these,
Oh,
but yeah.
okay.
But this could be helpful, guys. And I showed you guys that you can do this with Wolfram Alpha, right? Like Wolfram Alpha can do the same thing. It's just a lot more powerful when you guys have something that you can write other code into as well. Okay. What was another Laplace that we did that was kind of, I'm trying to think of some of the ones that we did that were nasty. Just regular Laplace, not inverse Laplace. But let me pull up this. This is our guided notes from. All right, let's see. How about this animal right here? Okay. So we did that. This is on guided notes number 14. Okay. That one we had to FOIL it out, and then we had to distribute. Okay, and then we had to find like the transformed of each of those. Okay, so that one was a little bit of a pain. So let's see if we can use MATLAB to be able to find the Laplace of that. Okay, so I'm just going to change the function. Well, I can just copy the code. So what I could do, folks, I can just copy this, and I'm going to change this to G just because I can. All right, and it was T times the quantity. All right, I'm trying to remember what it was. It was like e to the t and e to the t plus 2 e to the 2t. So, okay, so this would be expt plus exp 2 times t. And then we squared all this, right? All right, and I'm going to find the Laplace of g with respect to s. Okay, so I'll go ahead and run this. Okay, and there we go. We get this. Okay, it's pretty ugly, but it is what it is. I think in class, what we did was we just had like 3 fractions. Okay. What MATLAB did was it got a common denominator and added all those together for us. Okay. How nice of MATLAB. Of course, now it looks completely ridiculously difficult. Okay. We could probably do like a part frac and we could probably break that up. Okay. But I'm not going to worry about that. Okay. All right, guys. So questions about how to do Laplace transforms using MATLAB. Okay, really easy. What about inverse Laplace? Okay, so what's one that we had today that was really ugly? I'm trying to think of what we had. So I think we had this, like minus 1/2 s plus 1 over s squared minus 2s plus 2, right? And then eventually, remember, we did the completing square. We factored out negative 1/2. We split it up into 2, all right? And then 15 minutes later, we wanted to cry because it was all algebra. All right, let's see if MATLAB will do it a little bit easier for us. Okay, so I'm going to define a new function. Okay, let me call it Q, and Q is going to be this animal up here. Okay, so I'm going to say quantity of minus 1/2 times s plus 1 divided by the quantity of s squared minus 2s. Okay, so it's 2 times s plus 2. Okay. The function I'm going to use is I Laplace. Okay, so not too inventive, but inverse Laplace, I Laplace. I'm going to invert Q, and then the transformed variable is T. Okay. All right, now let's run this, see what we get. Okay, and there it is. Okay, that was a lot easier than what we did in class, right? Remember in class, it took us like 15 minutes. There, it took us 15 seconds. All right. So, so pretty cool that we can now find the inverse Laplace and you can check your answers at least. Okay. So I would encourage you guys when you're at home to check your answers either using your Wolfram Alpha or this. Okay. So that's literally the entire assignment, guys. Okay. So all I'm asking you guys to do is to solve the differentials by series, Laplace and inverse Laplace stuff. Okay, so I think there's like 2 or 3 of the inverse Laplace and Laplace for each of them. Okay, all right. So any questions I can answer about anything that I've asked you guys to do on this? Okay, I think what we'll do is we'll make it due not next Monday, but the following Monday. So that way it's after exam number 2. Okay, so due date for this would be. It's gonna be Monday, April. Who knows?
Like 7 minutes.
Well, our exam is gonna be on the 19th, right, guys? Because today's the
That's the
12th,
last thing,
right? So 19th. So then at 5, so it'll be 24th. Okay.
Oh, just the Monday after.
Right. Yeah. Yeah. I'm not gonna make you guys do the MATLAB before the exam.
Okay.
Okay. That's just inhumane. So. All right. So, other questions, guys? Got anything? Okay. All right, guys. So I'll post this on Blackboard for you all. Okay, so that way you can go back and relish